Welcome dear students, we are on the CEC Gurukul lecture and we are in the series of electronic circuit. In this electronic circuit, today we will discuss a very important component which is the Microelectromechanical System part 2, that is MEMS. MEMS are very important technology which is used to design the complex mechanical components with electronics using the batch fabrication methods. So, manufacturing is very important technique for the MEMS. So, how we prepare the MEMS and what are the characteristics parameter that we discussed in the last lecture. Now, current manufacturing techniques for the MEMS include surface silicon micro machining, bulk micro machining, lithography, electrodeposition, plastic molding and electro discharging machining are the manufacturing techniques for the MEMS, and these MEMS are manufactured by the many methods. So, some of the manufacturing techniques for the microelectromechanical systems we will discuss. Bulk micro machining we have discussed in the last lecture. This is the oldest silicon based MEMS technique. This method uses the entire thickness of the silicon wafer to build micro mechanical structures. The next manufacturing technique is the surface micro machining. This technique uses the photolithography to define the patterns that are then chemically processed to define the geometries of the thin films. Basically, this method used for the preparation of the devices of the micro and the nano size. Next technique is the LIGA, that is the lithography, electroplating and the molding on a single substrate. So, this is also used for the preparation of the micro and the nano devices. Another technique is the deep reactive ion etching. This is DRIE, and this is the new type of technology and it allows for the high aspect ratio etches into the silicon substrate. This used for the etching purpose on the silicon wafer or another type of the wafer also. Next step is the etching. This is also a process to remove the unwanted portions of the substrate using the chemical or the gas after photolithography. So, all these techniques are used for the manufacturing of the MEMS devices. Another is the hot embossing. So, we will discuss one by one. First, we have discussed in the previous lecture. The second technique is the surface micro machining. What is this? The surface micro machining is another very popular technique used for the fabrication of the MEMS. And there are large number of variations of how the surface micro machining is performed depending on the materials and the etchants combination that are used. However, the common theme involves a sequence of steps starting with the deposition of some thin film material to act as temporary mechanical layer on which the actual device layer are built. It means the first step, the development of the thin film on the device which we are using for the further purpose, for the further application, which the actual device layer are built on the substrate and followed by the deposition of the patterning of the thin film. Which pattern we require? We develop that pattern in the form of the thin film on the substrate will be deposited by using this method. And the device layer, thin film device layers of the material which is referred to as a structural layer, and this will be known as a structure layer, and then it followed by the removal of the temporary layer to release the mechanical structure layer from the constraints of the underlying layer. It means whenever the temporary layer we deposited on the substrate, that will be removed through the etching and thereby allowing the structural layer to move. The last texture, that will be the actual texture of that material of that structure that we required. An illustration of the surface micro machining process wherein an oxide layer is deposited and the pattern. Means we have a silicon wafer, then we just deposit the oxide layer, deposit on that substrate. This oxide layer is the temporary and is commonly referred to as a sacrificial layer. Subsequently, a thin film layer of the polysilicon is deposited and patterned, and this layer is the structural mechanical layer. First deposit the oxide layer and on this oxide layer, then the polysilicon layer is patterned, deposited or patterned according to the mask, according to the requirement on the wafer, on the silicon wafer. Then this layer is a structural mechanical layer. Lastly, this temporary sacrificial layer is removed and the polysilicon layer is now free to move as a cantilever. So, lastly, the last layer, that is the polysilicon layer, and that is also called the structural mechanical layer, will be used for the further purpose. And some of the reasons surface micromachining is so popular is that it provides for precise dimensional control in the vertical direction. It means we can control the dimensions of this structural layer, and this is due to the fact that the structural and sacrificial layers thicknesses are defined by the deposited film thicknesses, which can be actually controlled. We can control the thickness of the last layer. That's why this method is commonly used for the structure of the nano and the electronic devices. Also, surface micromachining provides for the precise direction control in the horizontal direction. Since the structural layer tolerance is defined by the photolithography etch process which we are using. Another benefit of the surface micromachining is that a large variety of structure, large variety of sacrificial and etchant combinations can be used in this process. Some are compatible with the microelectronic devices to enable integrated with the MEMS devices. So, if we surface micromachining technique, by using this surface micromachining technique, we can control the combination of the devices. We can control the structure of the devices, we control the dimensions of the devices. So, surface micromachining frequently exploits the deposition characteristics of the thin film, such as the by using LPCVD, and lastly we can say that surface micromachining uses the single sided wafer processing and is relatively simple. Means at a single side, one side we can use the wafer, and this allows the higher integration density and lower resultant per masking cost compared to the bulk micromachining. It means once a mask is prepared, so a bulk micromachining can be done. A bulk devices can be prepared by using this surface micromachining micromachining technique. You can see on the screen, you see that first step is the silicon substrate we are having, silicon wafer. After that, a 10 micrometer oxide layer is deposited. Now you see in the another diagram, you see that polysilicon is deposited on this silicon dioxide layer. After that, you see that the etching has been done, that the last part, that is the anchor cantilever, is remain on the silicon substrate. So, this is the process of the surface machining, and now this can be used for the further electronic devices. The most commonly used surface micromachining process and the material combination is the PSG sacrificial layer and that doped polysilicon structure layer, and we use the hydrofluoric acid as a etchant to remove the oxide layer, that is a sacrificial layer, and release the device, and lastly just it leave the poly layer on the surface of the wafer. So, this type of surface micro machining process is used to fabricate the analog devices integrated with MEMS accelerometer devices used for crash airbags deployment, and moreover there are the two surface micro machining polysilicon devices. Here you see this is the SAM images of the devices deposited on the surface, and that is further used in the at the micro or the nano level. Now, another variation of the surface micro machining is to use a metal structure layer. So, apart from the poly structure layer, we can deposit the metal structure layer on it. So, a polymer layer as a sacrificial layer, and on the O2 plasma as an etchant. If we use the metal, so the for the etching we use oxide plasma, so that it can etch the material, because the metal is hard, so we use the plasma for the etching. But in the in the oxide layer we use the hydrofluoric acid. Now, the advantage of this process is that the temperature of the sacrificial and the structure layer depositions are sufficiently low, so as not to degrade any microelectronic in the underlying silicon substrates. So, therefore, integration is easy by using this type of devices. Therefore, the integrating MEMS with the electronics are easy. Also, since the sacrificial layer is removed without impression in the liquid problems associated with this with the release of the etched material, and a process similar to this is used to produce the first was used in the Texas Instrument laboratories, and they used for the projection devices. Another type of method is the LIGA, that is the lithography method. So, another popular high aspect ratio micro machining technique is called the LIGA, which is the German acronym, that is the lithography, galvanoforming and Endform. So, this is the primarily non-silicon based technology. In the previous we use a silicon wafer, but this lithography can be done on the non-silicon substrate also, and it requires the use of the synchronous generated X-ray radiation. The sometimes is called the X-ray radiated technique. So, the basic process outlined we will see in the diagram, then how the special X-ray mask is used for the selective exposure of the PMMA layer using the X-rays. So, we use the X-ray radiation sensitive PMM onto a substrate deposition. So, PMMA is then developed and will be defined with extremely smooth and nearly perfect vertical side walls, and also the penetration depth of the X-ray radiations into the PMMA layer is quite deep and allows exposure through very thick PMM layers and up to and exceeding 1 mm. So, up to 1 mm we can deposit. After the deployment, the patterned PMMA act as a polymer mold and is placed into the electroplating bath, and the nickel is plated onto the open area of the PMMA. So, PMMA is then removed, therefore leaving the metallic microstructure, and this microstructure we will use again as a device. So, because LIGA requires a special mask and a synchrotron X-rays radiation source of the exposure. So, the cost of this process is relatively expensive, but again the bulk production is also possible by using this method. So, a variation of the process which reduces the cost of the micro machined parts made with this process is to reuse the fabrication metal in the step by step. as a tool insert to imprint the shape of the tool into the polymer layer. So, followed by the electroplating of the metal into the polymer mold and removal of the polymer mold. So, by reusing or by imprinting or by using this tool, so by using the masking, we can make this cost very easy. Obviously, the sequence of the steps eliminates the need of synchrotron radiation sources each time a part is made, and therefore significantly lowers the cost of the process. The dimension controls of this process is quite good, and the tool insert can be used many times before it is worn out. So, again we can do it in the form of the masking. So, you see step by step here, this is the process. The first the cast PMMA on the metal, and in the second step you see that is a radiation, you see clockwise, that is a radiation cast PMMA. Then next cast PMMA on the metal, next is the X-ray radiation deposited on the PMMA, you see there is a mask, PMMA mask, and then X-ray radiation is falling on that mask. After that you see that development of the PMMA through the X-ray. Now you see that is a particular type of the structure, a wing type of structure is there. After that the electroplate through PMMA is done in the fourth step. Then the removal is separate metal from the PMMA. So, now the final step we get the device in the form of the device. Now you see that this is the SAM images of the prepared material, a tall high aspect ratio gear made using the LIGA technique, and this is in the size of the 1780 micrometer. So, this is a very small device. Again your left hand side you see the high resolution, high magnification of this figure. So, you see that here we are having the that the gear is made by using the LIGA, and this is of similarly we can prepare the nano and micro devices by using this technique. Next technique is the deep reactive ion etching of the silicon, and this is used for the high aspect ratio MEMS fabrication technology. So, deep reactive ion etching or DRIE is a relatively new fabrication technology, and that has been widely used for the preparation of the MEMS, and this technology enables very high aspect ratio etches to be performed into the silicon substrates. So, side walls of the etched holes are nearly vertical, and the depth of the etch can be hundreds or even thousands of the microns into the silicon substrate. As we have seen the previous LIGA techniques where we have just prepared the gear, and it is also there is a large penetration and large etching. So, now we illustrate this deep reactive ion etching is accomplished with the dry plasma etch, and it uses a high density plasma to alternately etch the silicon and deposit an etch resistant polymer layer on the side walls. So, the etching of the silicon is performed by using a SFG chemistry, whereas the deposition of etch resistant polymer layer on the side wall uses the C4FS. So, mass flow controllers alternate back and forth between these two chemistries during the etch. So, the protective polymer layer is deposited on the side wall as well as on the bottom of the etch pit, because we are doing it in the deep form. So, the protective polymer layer is deposited on the side walls as well as the bottom of the etch pit. but the anisotropic of the H removes the polymer at the bottom of the H pit faster than that of the polymer in removed from the side wall. Means first the polymer will be removed from the lower part than the side walls. So, this side walls are not perfected or optically smooth, and if the side wall is magnified using the SAM inspection, a characteristic washboard or the scalloped pattern is seen in the side wall, and the H rate of the most commercial DRIE system varies from 1 to 4 microns per meter, and DRIE system are a single wafer tool, as we have done in the previous LIA. So, LIGA, so DRIE also a single wafer tool. Here photoresist can be used as a masking layer for the DRI etching. So, photoresist we will use when we use the etching here in this process. So, selectively with the photoresist and oxide is about 75 to 1 or 150 to 1 respectively. For a wafer etch is relatively thick, photoresist masking layer will be required. You see on the right hand side we are having the, here we are having the SAM image of the deep DRIE method. So, a SAM of a MEMS component fabricated using DRIE and the wafer bonding, and this device was made using the SOI wafer, wherein the backside HR was performed through the handle wafer. You see that there is a hole and that etching has been done, and you can see that the backside edge was performed through the handle wafer and stopping on the buried oxide layer, and the front side DRI was performed on the SOI device layer. So, then the buried oxide was removed to release the microstructure, allowing it to the freely moved. Another you see a cross section SAM of a silicon microstructure fabricated using the DRI technology, and as can be seen that etch is very deep into the silicon substrate and the side walls are nearly vertical, and that etching has been done by using the DRI method. So, the aspect ratio of the etch can be high as 30 to 1, but in practice tends to 15 to 1. The process receipt depends on the amount of exposed silicon due to loading effect of the system, with the larger exposed areas etching at a much faster rate compared to the small exposed area. The larger area will be exposed more. Consequently, the etch must frequently be characterized for a exact mask feature and the depth to obtain desirable result. So, in this method the masking is important as well as the depth measurement is also important to get the desired result. So, this method is used. Now, you see on the screen that how etching deposit polymer is done. Now, you see first step is there silicon and there is a mask, and then etching has been done, and then you see the polymer NCF2 is deposited. After that you see that part is etched where the polymer, the deposit polymer will be remain on the where it is required. So, this is the etching process has been done. Now, the SAM and MEM devices fabrication using the two-side DRI etching technology on a SOI wafer. This we have discussed that this is the SAM of the cross section of the silicon wafer, demonstrating the high aspect ratio and the deep penetration that can be fabricated using the DRI method. So, now we will discuss next in the next lecture regarding this MEMS and how we will fabricate this MEM by the another methods also. Thank you very much.